based on what's going to happen. So zinc is going to, it is the anode, so it's going to be doing what?
It's leaving.
Going to be oxidized or reduced?
Oxidized.
It's going to be oxidized. So zinc is going to become Zn2 plus 2 electrons. This is where you added the zinc, tap, 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 into the copper. If you actually, we have ORP sensors, oxidation reduction potential sensors. If we put an ORP sensor into that solution we were doing yesterday, it'll actually say, yep, there's oxidation reduction going on. Yeah.
How does that work?
It was the red one.
How does it
It was,
work?
It was here. Let's make this better. Let's make zinc black because zinc didn't have a color. So the zinc that went in became Zn2 plus, and it gave off 2 electrons. The copper that came out started as copper 2 plus. It picked up those 2 electrons, and it became the brown copper metal.
So zinc is oxidized.
So zinc is oxidized, copper is reduced. Okay? Now we can look at this and say, all right, I'm getting way ahead of myself. I'm going to leave this here and come back to it. Okay. Now, the salt bridge. You need to have some way to separate the cells, but still allow the electrons to flow, and still allow the charge to be balanced. Okay? So in this diagram here, the electrons are flowing, but that would mean if this porous bridge or salt bridge is not here, that would mean the electrons would pile up over here, and you have a very negative solution, a very positive solution, and that wouldn't work very well. So we have what's called a salt bridge or a porous bridge, and that allows the ions to travel across. So if negative ions are going this way, sorry, hold on, if electrons are going this way, then negative ions are going back this way. Does that make sense? Or you might have cations also traveling the same direction. Charge must be conserved. So if electrons are going this way, then negative ions have to go back the other way to balance it out.
Can you do that together?
Yes. So if electrons are going this way, ions, so right, imagine this says electrons, imagine this says ions, so this way. If electrons are going this way, then ions are going the opposite way to balance out the charge.
Wait. Do they like go over? Do the electrons go?
The electrons are going through the wire, and the ions are going through the porous barrier.
I thought that was just like an arrow, and I was like, how do they go?
It's a wire. So we could actually put a light bulb here, and we could get electricity, or we could put a cell phone here and call your mom.
And the purpose of
Or text your mom about the coronavirus.
The purpose of the what?
The purpose of that is
The porous barrier keeps the cells separated, so they don't mix, and it allows the ions to travel. Yeah. So in our lab last year, we just dumped the zinc right into the copper, so there was no porous barrier. The electrons were just jumping across. But we could have actually put a porous barrier in there, and we could have harvested electrons during that process. And that's what we're going to do in lab. We're going to get a piece of zinc and a piece of copper. We'll stick the electrodes. The multimeter will become the wire, and the little piece of paper will become the porous barrier.
What do you use that for?
Flashlights. We're not going to make enough voltage to actually, so anything, like texting your mom, doing calculations on your calculator, we're not going to actually make enough potential to actually be useful.
Not just another way of transferring energy.
But it will be useful to
So this is basically in an old battery, they would have 2 pieces of metal wrapped up, and you'd have like a spool of like a cinnamon roll of metals. So you'd have enough metal in there that they would actually give you useful voltage. But we're going to have like postage stamp squares of metal.
Do you need any liquid at all, or can it just be metal?
We definitely need to have a concentration. There needs to be somewhere for these ions to be. So you have to start in aqueous and in aqueous. Okay. Does that make sense so far?
Yes.
Okay. Cool. All right. We're going to move on?
Yes.
Moving on. Okay, some redox terms. I think we already talked about this. The thing that gets oxidized is the reducing agent, or the reducer. The thing that gets reduced is the oxidizing agent, or the oxidizer. Okay. So what I'd like you to do is really quickly identify the redox pair, or identify the redox pairs in these cases. Which thing gets oxidized? Which thing gets reduced?
The Na gets oxidized.
CL.
So these both start at 0, then Na becomes
They
plus 1,
get-
plus 1,
Plus plus.
plus plus, Na becomes plus,
Get oxidized.
chlorine becomes minus.
Or-
Yeah.
What? Oh.
So sodium is the,
Oxidizer.
so sodium gets
Oxidized.
oxidized,
Yeah.
Is the
so
reducer.
is reduced, sorry, is the reducer.
Yeah.
Chlorine gets reduced,
So it is
the
so
oxidized.
is the oxidizer. Okay, zinc, this is the reaction we did last year. Zinc becomes zinc 2 plus, copper becomes 2 plus to 0. So zinc gets oxidized, therefore is the reducer. Copper gets reduced, therefore is the oxidizer. And same thing here. Only in this case it's backwards because silver is actually less stable, is less active, more stable. It's less active than copper. So in this case, when you put copper into silver nitrate, the copper gets oxidized and the silver gets reduced. This is that little tube, remember the little, I did the demonstration with the copper wire and the silver crystals came out? You can download it on YouTube. So, there you go.
Whoa.
Yeah, look at that. Look, it's an animation. Whee! Animations are fun.
Do silver elements cost a lot?
They do. Yeah, silver nitrate costs quite a lot. You get it in very small quantities.
Do gold elements cost a ridiculous amount of money?
Probably. I don't have any gold compounds, so probably vastly more expensive than silver. It's to the point where if I tried to order it, some people are like, why do you need gold? I want to make everything gold. Alright. Alright, so half reactions. These are half reactions. So a half reaction is simply, let's skip that one. Oh, here we go. So half reactions are simply the oxidation half and the reduction half. And that's actually what they're called. The oxidation half reaction, the reduction half reaction. So this is the oxidation half reaction, this is the reduction half reaction. Now they should balance, but they don't always. Sometimes you have to balance them by adding numbers. Okay. Sometimes you'll get something that takes 2 electrons and you have a reaction where the other thing gives 1 electron, and you'll have to balance it. But this is the oxidation half reaction, the reduction half reaction. There's a lot of redundancy because, again, I just edited this yesterday. Okay. Does this stuff make sense?
Wait.
Okay.
Half reactions.
We've actually done these before when we did the redox titration in lab. But yeah.
Wait, is it just when you add the electrons? Is that count as a half?
Yeah. So the half reaction is basically just the ion and the metal and the
Then you
electrons.
can't have it on. You can't go from like Cu2 plus to Cu plus 2. Like they have to be certain.
Okay, remember how I said cross out where it's Cu2 plus going to Cu plus 1?
Okay, well I mean, okay, you can wait for any of this.
Yeah.
They need to be. You can't subtract your electrons. That's what I.
Correct. Okay. So yes, you never subtract anything. Yes. You never subtract. You only add. So in this case, guys, this is the little crystals on silver crystals on the copper wire. In this case, copper needs 2 electrons, or copper produces in this case. This is oxidized. Copper produces 2 electrons, but silver only needs 1 electron to balance it. So the half reactions for this, you basically have this. But you'd have to double the half reaction for silver to make them balance. Make sense? That's why you're like, the silver, the coppers, and all that stuff. So you're going to need 2 silvers for every 1 copper. Every 1 copper you oxidize, you're going to reduce 2 silvers. Cool? We haven't even got to the first equation yet. All right.
Let's get to it running.
Okay, so does this make sense? Because we have like a minute left. I want to talk about standard, and then you can do your next page of the packet. Okay, standard reduction potentials. When you hear the word, or see the word, or read the word standard, it means 1 molar, 298. Okay, we talked about this before. 1 molar, 298. So reduction potentials are based upon hydrogen. I have a cool little video which I'm not going to be able to get to. So reduction potentials are based on hydrogen. Hydrogen gets 0, and you actually notice on your chart where it says 2H plus 2E becomes 1H2, 0 volts. So they needed a standard upon which to basically view everything. They made hydrogen that standard. So hydrogen has the standard electron potential of 0. When you hear standard conditions, that means a 1 molar cell, 1 molar 2 plus, 1 molar zinc 2 plus, and 298 Kelvin. 25 degrees Celsius. Okay. And no, I don't have any platinum electrodes.
Oh.
I know.
Wow.
Yeah, I don't have any platinum electrodes.
Platinum.
Platinum is the single most,
This says Boulder City.
I know. Platinum is the single most not active metal you can get. It'll even kick out gold.
Ooh.
Yeah. Did I put it on my activity series? Oh no, I'm wrong.
Sponsored
I put gold. I put gold below platinum. So sorry, I put gold below
by
platinum.
Nike.
Platinum is
Sponsored by
more
Nike.
active than gold.
We just whipped it.
All right. Questions for today?
Just has a Nike.
How much
0
of
volts.
the package
Made out of
needed?
like
The next unit, so that's 9,
vibranium.
3, 9, something.
Wait, so the last, the
934.
least active, the more likely it is to pick something out? Or the more likely it is to get kicked out?
Get kicked out. More